Now, because reaction rates are monitoring the concentration with respect to time, we can look at this graphically. If we look at this particular reaction of A molecules going to B molecules, we can monitor the number of molecules over time. So in the first 10 seconds, we've consumed 10 molecules of A, and we've produced 10 molecules of B, which reflects this one-to-one ratio that I have right now. Now, the rate of the reaction, or the change in concentration of the substance with respect to time, is actually going to be the slope at of the tangent at a given moment of time. So if we want the rate of reaction, we need to take the slope of the tangent. Another thing to consider is what would happen if we changed the stoichiometry of the reaction. So if instead of producing 1 mole of B, we produced 2 moles of B. If that were the case, as 10 molecules of A were consumed, rather than making 10 molecules of B, we would make 20 molecules of B. So that's going to affect the steepness of the reaction. So in this case, B is being made at double the rate, or twice as fast. Okay, so if you look at the slope of the tangent here and the slope of the tangent there, okay, in the second example, it's going to be double. So just a couple of things to consider here. The rates of the reaction are going to reflect the stoichiometry, and the rate of the reaction, if you want the instantaneous rate of reaction, it's going to be the slope of a tangent at a given moment in time. Okay, this gives you specific rates, okay, for a specific reaction. It gives you the concentration and time. And what they did was found the slope of the tangent at given moments of time. And what you can see is that as time has progressed, you can see visually from the slopes and also with the values, the rate of the reaction actually decreases over time. Okay, so these aren't linear relationships. The rate of the reaction is going to decrease over time because as the reaction proceeds, the amount of reactant and product that you have is decreasing. So the number of effective collisions that you have is going to decrease as well. Okay, so it makes sense that the rate will decrease over time. What we want to be able to do, you want to be able to visually look at a graph and understand how the rates are connected to the slopes of the tangents. You're not necessarily going to need to calculate the rates of tangents, but understanding them overall is very helpful. More importantly, though, you need to understand that the rates of individual reactants and products are connected to their stoichiometry. Okay, so as you can appreciate, the products are always going to have a positive rate of reaction because their concentration is going to increase over time. And the reactants are going to have a negative rate of reaction because their concentrations are going to decrease over time. We're going to use the stoichiometry to relate the rates of one reactant to another or to a product. So let's look at an example here. We've got this reaction 4NO2 plus O2 going to 2N2O5. Says, suppose that at a particular moment during the reaction, the molecular oxygen is reacting at a rate of 0.024 mole per liter per second. Okay. So rate is the change in concentration over time. So that's why the units are molar per second, which is really the same as mole per liter per second. Okay, change in concentration as a function of time. When you know the rate of one particular substance, so in this case we know the rate that oxygen is reacting, 0.024, we can determine the rate of something else. So we can determine the rate of formation of N2O5. The ratio between these is 1 to 2. So N2O5 is going to be produced at double the rate that the oxygen is being consumed. So the rate is 0.048 mole per liter per second, or molar per second. The rate at which the NO2 is reacting is negative 0.096 mole per liter per second. It's got a negative rate because it's a reactant and it's being consumed, so its concentration is decreasing over time. And it's 4 times the rate of the oxygen being consumed because the ratio between them is 1 to 2. Okay, so let's look at one more example here. Molecular hydrogen is being consumed at a rate of 0.074 mole per liter per second. At what rate is the NH3 being formed? So we know the rate of the H2. We know that for every 3 H2 is used, we produce 2 NH3, and the rate reflects the same ratio. So applying the 3 to 2 ratio, okay, we find that the rate of production of NH3 is 0.049 mole per liter per second. Looking at the consumption of N2, it's reacting at a rate of 0.0247 mole per liter per second because the ratio between the nitrogen and the hydrogen is 1 to 3.